All right, so our next speaker, Mr. Armin Tajirian, has over 45 years experience in providing consulting materials engineering services to the construction industry. Services include failure analysis, structural investigations, evaluation of unreinforced masonry buildings, earthquake damage assessments, environmental assessments, architectural investigations of building envelopes, evaluation of concrete problems, materials testing, specialty inspection, review of plans and specifications, and R&D of new products. In conjunction with above work, Mr. Tajirian provides support to structural engineers, architects, building owners, contractors, insurance agencies, building managers, and other consultants. He has provided expert witness testimony in construction-related litigation cases. Mr. Tajirian has also acted as project manager to lead a team of engineers or other professionals on multi-phase consulting projects. Typically, a project would go through an investigative phase, followed by a comprehensive written report with recommended remedial work phase, and finally, an inspection of remedial work phase. In his forensic analysis, Mr. Tajirian frequently uses non-destructive testing to evaluate construction materials. Equipment he utilizes include ground-penetrating radar, ultrasonic testing, Schmidt Hammer, moisture meter, and borescope. And I just realized that everybody has a copy of this, so they have probably read it on their own. So if there's anything you'd like to add, please feel free.
I'm the best guy with GPR, so that's the only.
Yes, and we're going to have a demonstration. Is this
Yes.
high enough for you?
Yes, thank you.
There we go.
Thank you, Sherry. You're probably fed up with listening by GPR, but I've just got a few things to add to what Mark said, and it really has to do more with structural engineering, and everything's above grade that I'm going to talk about. Mark was talking about stuff below grade. That's something that we don't do, and I have avoided that type of work. I will start off by some basic science, and I hope this is not too difficult or boring for some of you, but let me try this out. If I was to ask you who you thought was the most influential physicist throughout history, you might think somebody like Isaac Newton, who was influential in giving us the theory of gravity, or you might cite somebody like Albert Einstein, who's eponymously named after, this room is named after, or excuse me, Stephen Hawking is a contemporary of ours who has done work on the black hole theory, etc. So those would be the prominent people you might think about. But in reality, we as engineers, architects, and materials scientists really should give a lot of respect to a man who brought about something that everybody uses, pretty much all of us, on a daily basis, and that is the theory of elasticity. That man is Thomas Young. Thomas Young was born in the late 17th century in England. He trained as a physician, later turned to science and became a physicist, and he formulated what we now call Young's modulus, also known as the elastic modulus, but I'll call it Young's modulus. And I'd like to start off by just showing you something before we go to the first. Where's the clicker? Sorry.
Oh.
Oh.
Yeah.
Is the remote still on?
It should be, yeah.
Okay. Is it working?
Yeah.
Okay.
And if you, yeah. So the center is the pointer, and then this is forward, backwards.
Backwards, okay, thank you. So let me just show you this. If I were to take a material such as this rubber band and pull it with a force of, say, 1 pound, I'd get a 2-inch extension. If I were to pull it with another force, with another pound, let's say that's 2 pounds, I'm up to 4 inches in extension, also elongation. This is what the theory of elasticity is about, that we have a direct relationship between force and elongation. Now, the beauty of it too is, and this is where Young's modulus comes in again, is that when I release this force, it goes back to zero. Elasticity is the elongation where it is directly related to the force applied. In my first slide, I'm showing what is known as Hooke's law. Prior to Thomas Young coming into life in England at the time, and this is now the end of the 17th century, engineers used Hooke's law as a basis for doing analysis. Hooke's law basically okay, this is the basis of Hooke's law. Force equals K times D, where K is a spring constant. I showed you the rubber band, what I was talking about, and that is when you pull it a distance. What I was talking about 1 pound and 2 inches, etc. But there is this direct relationship. The force equals the constant, spring constant times elongation, and that is the Hooke's law. And as I said, up to the end of the 18th century, that was the basic equation engineers used to make determinations on calculations, etc. So along comes Thomas Young, and what he does is as follows. He says that there is a requirement that when you are trying to find out how material is going to behave, that this K, the constant, is basically related to the material that you're testing. You need to know the area of the material. You need to know the length of the material. So in order to avoid all this, he formulated what has become known as Young's modulus. Young's modulus basically takes out the force by substituting the stress times area, and takes out the delta, the T, the deflection, by substituting elongation times length. And then if we substitute the K L over A with E, which is the elastic modulus, we get this formula down here: elastic modulus, or Young's modulus, stress over strain. Stress over strain, now as a basic material equation, does not require us to know what is the property of the material that we are considering. And for example, in concrete, we are basically looking to see, in structural analysis, we're looking to see how much stress is generated in a member, typically a flexural member, compared to the strength of the material. So the stress is what we are calculating, and that is where this Young's modulus comes in. We want to know whether this stress will actually be greater or less than the strength, and that will tell us whether that section of material that we're designing for is adequate or not. So the basic information that we got from this whole process of what Young's did was to now have a relationship that has nothing to do with the dimensions of the material itself. As we talked about in the spring itself, you recall we had an L and we had a delta or a D, and that we needed to know what the L and what the area are in order to establish that. Okay, so next thing that I want to impress upon you is this relationship between what is elasticity and the equipment that we use typically in our non-destructive testing. And I'm only talking about non-destructive testing from here on out. Okay, we are sending basically either signals through a material, and I'll go through that in a minute, or we are using the Hooke's law type constant and a spring in order to establish these relationships. The most important thing I want to leave you with at the end of today, if I can, is that most of what we are doing is density related. We are, with all these tools, we are looking to compare a certain density to another. And that's what establishes what we're looking at. And for example, density of concrete, which is what we're doing when we're using GPR for us, is around 150 pounds per cubic foot. The density of steel, which is what we're trying to establish whether it's there or not, is about three and a half times that. So this difference, this large difference in density, is what actually establishes the images that we will see with the GPR and we've used. Mark Olson just earlier talked about the dielectric constant. In GPR, the real difference between one material and another is called the dielectric constant. But dielectric is directly related to density. So in order not to confuse this whole issue in your own mind, just keep at the back of your mind that it's a density issue that we're looking at. We're looking to see how one density compares to another. Finally, I'll also show you something, a piece of equipment they use where we use pulse velocity. Pulse velocity, again, is a sound wave that we send through material and then pick up the image. And with that image that we pick up, we'll know what the speed of the pulse velocity was through that. For instance, in concrete, the average velocity of sound through concrete is about 12,000 feet per second. And knowing how thick the member is that we're looking at, and I'll show you I'll demonstrate with the equipment, then it'll be easier to figure this out. But what we can then calculate based on the equation of speed equals distance over time, we can calculate how long it's going to take for that sound wave to go through the concrete from one side to another. So those are the basic elements that we're looking at. But like I said earlier, density is what you should keep at the back of your mind, because that's really what we're talking about. Okay, here's GPR data. This is the most recent sophisticated piece of GPR we use. It's a small handheld piece of equipment. Mark Olson showed you, I think, photographs of it, or one photograph of it anyway. But I want to show you how simple it is. It is a cart, it's got wheels at the bottom, and you just push the cart along the surface. It could be along a slab, and I'll demonstrate this later on, or along a wall, and the cart picks up an image. And the way it does it is it sends a signal from one side of the cart into the concrete or whatever the material is, and then that comes back. And it's the dielectric constant of the material that we're looking at that really tells us what it is. But the basic principle is that we generate a set of hyperbolas. So in the top, just looking at the top graph here, this is a cross-section through a slab. This shows the top of the slab. This hyperbola, which shows the intensity of the steel that we just picked up, is because of its maximum. That is where the rebar or the steel is. And then you can see one here, one here, one here, etc. So the way we do it is we push this cart along the surface. Let's say it's a concrete slab, and we'll pick up these hyperbolas. And these hyperbolas, when we pick them up, we mark them up on the slab or on the wall, and that tells us where the rebar or the post-tensioning or the conduit is. So it's very simple, but I want to warn you that it is something that is operator sensitive. Not everybody should be using this without going through a class on this. So that is at the top. We have a typical basic GPR survey result. And this, again, as I said, will come out on this small screen here. That'll show us these hyperbolas. So it's very easy to use once you get to know how to do it. Now, as we become more sophisticated with this, we can go down to the lower chart. And this shows that not only can we pick up rebar or PT cables, it can also pick up conduit. And it also picks up plastic or metal, and also shows us the bottom of the slab, which is very important. So we don't even need to measure the thickness of a slab or a wall. We can just run a GPR, and where the change in color occurs, that tells us the thickness. Along here, the vertical axis that is the thickness. So that is telling us, for instance, this first peak of the parabola is down about 2.9 inches. And that is telling us that the slab here at the bottom is 6 inches. Thickness of the slab or the wall is established with this GPR. So this is an extremely powerful tool. And we can also use it for other things like wanting to look for voids in concrete, which are not really that easy with the GPR, but it can be used to a certain degree. I can talk about that later on.
How do you know what is plastic and what is metal?
That's why I'm saying this is very sensitive to the user. Only people who are experienced in this will know. I can't show you here, but one of the issues is the parabola, the hyperbola, excuse me, has an intensity. When you get steel and it's very narrow like that, then it's a different material. As you get, if the density of the material becomes higher and higher, then it's more likely to be a pointed material, and then it flattens out. Okay, so again, this is only to be evaluated by people who've done this for many years. Otherwise, because conduit is a very difficult subject, as I'll show in a minute, what we're really using this for mainly is to find out where this rebar is. One, to determine the spacing, but more important because people are using this tool to core, to core or to drill through walls or slabs. And you don't want to be hitting a post-tensioning cable. Hitting a post-tensioning cable could cost anywhere from $15,000 to $30,000 to repair. So anyway, I will just go on to the next slide. Prior to GPR coming onto the scene, which was about 20 years ago, we used to use X-rays to find out where the rebar is in steel. The rebar is in concrete. This image is of an X-ray. Now, this is X-ray just like you would go to a doctor if you broke a bone or something. And it shows you through the concrete what the materials that have higher density in focus. So we've got here steel, 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 crosswise in the center. This shows us where the steel is. And it will, the intensity of what you're looking at actually is developed through the equipment that you're using. So this could be higher intensity or lower intensity. But as you can see, that the larger the density, again, density, this is more prominent, a lighter in color material. So this is all concrete. This is concrete, concrete, concrete. And these lighter lines are reinforcing steel.
Can I ask you a question?
Sure.
How do you determine a layer of steel? Top layer, bottom layer, can you determine that?
Yeah, good question. Well, with the, let me answer first with the X-ray. The X-ray is hardly used anymore because that's one of the difficulties. But the X-ray had a beauty to it because if you knew the thickness of the concrete and you knew that this you could measure with on your X-ray this distance, then by similar triangles, you can find out what the size of the rebar is, okay? So if we took an image and there were various diameters here, okay, this would be an indication that these are the different layers. But you need to know where, you need to know, you know, if you do these triangles, sorry, if you do similar triangles, then you need to know what the depth of the rebar is. Then you can tell what the diameter of the bar is. If you had another layer here, then it would show as a larger or smaller, depending on where the depth is of the rebar. So that's it. But in general with GPR, and this is actually a somewhat of a problem, is that the GPR on its own cannot tell you what the diameter of a bar is, unless you have something to compare against. So typically when we do the scans, let's look at the top one here. Oh, sorry. When we're doing a scan, this top image tells you where the bar is. So you can, on an XY axis, you know where it is exactly. And you know how deep it is, because we can, I don't have it on the scale, but you know how deep it is. But you can't tell the diameter. So what you have to do is chip out one location. Once you've done that, and you know what that bar diameter is, then you can tell what the rest of the bars are in that configuration. Okay, so that is a slight limitation with the ground penetrating radar. Okay. Can anybody tell me what you think this might be? Excellent. Okay, this is an image. When you go to a dentist, and the dentist takes an image, an X-ray image of your teeth, this is how it shows up. And this is exactly like the concrete image I showed you previously. See that? And this, it's a difference in density. These are actually my teeth at a recent dental. And here's the thing. This material down here, that's your gum. This material here that's slightly darker in color, that's the tooth. And this material that's very bright, that is the filling. So this is an example of how this X-ray works. It's basically a color difference. And you can use this image, this type of image, to investigate concrete, slabs, conduit, rebar. All these things can be done because of this imaging. So this is a very powerful tool. The GPR and the X-ray are very powerful. Now, the problem with the X-ray, as maybe most of you know, is that you need to protect around it when you actually shoot. So that's why when you go to a dentist, they always put this cover on your chest to make sure you don't get any of the X-rays into your body. But GPR doesn't have that constraint because it is totally, it's totally okay to do, and it has no consequences that are could harm you physically. So these are the I wanted to talk about. These are the issues I wanted to talk about in terms of X-ray and GPR. This slide is of a Schmidt Hammer. A lot of you are probably familiar with the Schmidt Hammer. Schmidt Hammer tells you, gives you a relationship between compressive strength of the concrete through this here, this part of the Schmidt Hammer registers a number. So we have a number like 30 or 25 or whatever. And then we have a chart which tells you if it's, let's say, 25, it's 3,000 PSI concrete, etc. The beauty of it is it's non-destructive. Otherwise, if you wanted to know, what is the concrete compressive strength? You have to take a core out. And we don't want to do coring unless we absolutely have to. So Schmidt Hammer is good for that. It's a non-destructive technique, and it gives you the compressive strength or the tensile strength of the concrete.
Do they have one of those for masonry? Yeah. Do they have Schmidt Hammers for reinforced masonry?
You know, you could make one, invent one, but there probably is not enough of a need for it. I mean, it's just a calibration of the spring constant. It's the same spring constant that I showed in that first slide, which was showing the F equals the KD relationship. Spring constant tells you what the force is. Now, if there was enough demand on it, yeah, you could have a Schmidt Hammer for any material, brick, clay, block, whatever else you might do. But typically, because most people are only interested in concrete, that's why the Schmidt Hammer is really for concrete use. Sure.
I seem to recall there was a device in metallurgy, a Rockwell C hardness tester.
Yeah.
Same thing.
It's basically the same principle because it's the energy you impact into it that tells you how much, what the strength of the material is. With the Rockwell hardness, you're impacting energy into the metal, and you get the resistance, and that tells you what the material strength is.
With respect on the rebar scanning, what's the difference between, obviously, the GPR, the X-ray, those are two technologies, but picometer, we're going to talk about that later? No,
I'm not going to talk about picometer because that's really old technology. Picometer also locates rebar. So if we were to go back here, a picometer will, if you scan the top of that, I think this is a slab, I believe, you have to scan it, you can see those lines, okay, with the tachometer. And the way it works is it's got a needle, and when the needle goes up to a maximum location on the scale, comes back at the maximum point, that is where your rebar is. So as you scan along a slab, goes up, and then just before it comes down, you know where that rebar is. And we're also talking about two senses, the X and the Y direction. So even with GPR, which I forgot to mention, we're talking about X and Y direction. You scan in both directions. You can't pick up both the X and the Y at the same time. The intensity only comes in unidirectional. So
the tachometers, are you sound waves, or what is that used?
the tachometer?
Yeah.
No, the tachometer is electromagnetic.
Okay.
The GPR, ground penetrating radar, is based on radar. Radar is I'm not into physics, but basically it is a wave that's sent through and picked up again. I'll talk about something a little bit later on. Maybe we can discuss that further. But yes, sir.
So for the Schmidt Hammer, the picture you showed was a nice smooth wall. Can you use it on rough concrete?
No, the Schmidt Hammer has a major issue, and that is it is measuring the strength at the surface. It doesn't measure through the concrete. So if you want to measure the compressive strength of the concrete or whatever material it is, you need to take a core out. But the Schmidt Hammer just gives you the surface strength, and that is a little bit of a problem with Schmidt Hammer, because it could be that the cement paste that was used in that particular mix is extremely hard. So you pick up really a lot of strength on the surface, but inside, within the concrete wall or slab or whatever, it could be weaker. So that is one of the issues as to limitations of the Schmidt Hammer. The coring and getting a core out to test is really the best way to figure out what the compressive strength of the concrete. But we're doing non-destructive testing here, so I don't want to talk about coring here. But anyway, that's yeah. But it's also, the Schmidt Hammer actually is a very good tool for comparison purposes. So let's say I know the compressive strength of this slab here is 3,000 psi. I can go to another location on the slab and measure just with the Schmidt Hammer. So I took a core out, I did a Schmidt Hammer, I know it's 3,000 psi, and on that needle it's registering about 30, let's say. I go to another location and I use the Schmidt Hammer, and the Schmidt Hammer reading will give me an approximate compressive strength of that concrete, because I can do a comparison. Yeah. Go ahead, Brian.
So with the GPR, I know we can use it for non-destructive testing, just to find the location or spacing of rebar, but to get exact measurements on depth, don't you have to take a core and at least know that?
No. The GPR, the beauty of it is it tells you what the depth is. The GPR works on the principle of intensity of energy. You send energy down through, I'll demonstrate this in a minute, and you pick it up. So you send it down on one side, goes down one side, picked up on the other side. So it's like this, and the distance it travels tells you what the depth is. So with the GPR, we can tell let me just go back. Here, you see on the left-hand side, the column on this side, that tells you the depth. So we know that this particular bar or this particular conduit here is at approximately 3 inches. This one down here is at approximately depth of 4.5 inches. I don't know if you follow.
Oh, yeah.
So the beauty of it is it tells you what the depth is. You can tell what the depth is with the GPR. But what you can't tell is the diameter. That's the unfortunate part.
We just based on I went to training on this as well, and
Yeah.
you need to calibrate it for each concrete slab or wall you're working with.
No, you don't need calibration. It's already pre-calibrated. What you're measuring, again, is energy that's sent down into the concrete, and it's picking up a different type of energy when it hits steel. Now, it's possible, we had plastic conduit, other materials too. So when it bounces off of that tells you where the location is. You can't tell when you're doing scanning. This is what you see. I'm just showing this because to kind of highlight what it's capable of. this is what you see. So you can't really tell what these peaks are. The only way you can tell, well, we use it primarily for locating post-tensioning cables. Because as you probably know, coring post-tension concrete and hitting the post-tension cable is a very expensive repair, $15,000 or whatever. So when you're scanning, that's what you see. I'll show you a little bit later on when I do the slide here. Excuse me. So what we can see is these peaks, these parabolas, hyperbolas, and it shows on it the depth. So that one we know is at approximately, let's say, 2 inches from the top. This bar is approximately 3 inches from the top, etc. That's what it tells. You can't tell at that point whether it's a conduit, it's some other metal object, but it can't tell you where it is. And I might just add, sorry, just one thing. This equipment really needs somebody who's sophisticated, done this many times. Repetition with this GPR is what makes it work and beautiful. Somebody like me, let's say a novice does, I haven't used it that many times personally, will always have difficulty because there's a learning curve in it. But if you do this every day, then it becomes pretty obvious. Is this, rebar? How deep is it? And whether it's a rebar or plastic conduit or a metal conduit. Okay, so is there another question? Sorry, I got
back to the Schmidt Hammer really quick. What's the difference that you've seen between the surface concrete and the inner core concrete? What's the biggest delta that you have seen, and what would you estimate as a conservative deduction off of what you would read off of the surface?
That's a good question. It's very difficult to tell. The surface concrete that you're actually hitting with the Schmidt Hammer is measuring the strength of the cement paste in the concrete. Cement paste could or could not be the determining factor of the strength of the concrete. And as we know, compressive strength of concrete is really dependent on the water-cement ratio. So it's possible to have a really low water-cement ratio right at the surface, but inside, within the member itself, is not that strong. And this is the problem with it. Whereas when you core, you take a core, a 4-inch, 6-inch, whatever diameter core, and you bring it back to the lab, then you're testing the entire section. So the surface strength does not play a role in this determination.
So if you return 4,000 PSI, me saying, I'll assume 3,000 or 1,500, I mean, it's just off the table beginning to say.
Yeah. I want to, did you want to say?
We never use it for qualitative measuring. We use it, quantitative. We always do it for comparison. And we have used it on these three, but we do it, what is it, reading over here compared over here to over here to tell us about conditions or something like that. But we don't use it as an absolute measuring tool.
You're absolutely correct. And plus, there is here a scale that tells you what the rebound number is. And then there is what plus or minus for these readings, which is very important. So you read, let's say, a rebound number of 30, and the 30 is 3,000 PSI, but it's 3,000 PSI plus or minus 25%. So you've got to keep that at the back of your mind, that it's not really the best tool to determine what is the compressive strength. Just like the lady said, it's good for comparison purposes. So I measure the strength here, and I go, let's say, 10 feet away, and that rebound number 10 feet away will tell me whether there's a problem either here or 10 feet away. So it's good for comparison purposes, but not really the best for saying this is the compressive strength of that concrete.
Why nobody performed a study on that?
Perform what?
To compare core strength and sheet hammer.
Yes, we do that. Let's say we have a large slab, 50,000 square feet or something, and the client doesn't want you to go coring everywhere. So what we do is we take one core out, we run a Schmidt Hammer there, okay, and then the other 10 locations, we just use a Schmidt Hammer. So excellent, that's an excellent point. That's one way of using it. But like, well, the trouble with it is, it's not as definitive as taking a core or compressor. If you're wanting to do something a plus or minus, yeah, that's fine. And like you said, do one location, do both, and then use that data to interpret for the rest of the structure. That's what we would do. And how are we doing on time?
You think you can do it in 10 minutes?
I'll start running. Now I want to show the equipment actually. Sorry, I may cut this short. Let me just show you. This is a moisture meter used primarily for wood. Again, we were talking about, this has got two prongs. I've got one here just to show you. Again, the way it works is that you send an electric signal from one prong, comes down the other, and measures the amount of moisture in wood. We use on plywood and, on any wood for that matter. So I would like now to do some demonstrations before I give you some case studies. GPR. This is a very powerful tool. And like I said, the way it works is it's a cart, it's got wheels, and we will move this cart along either a wall or a slab to determine where those hyperbolas were. The hyperbolas tell us where the reinforcing steel is. It takes a few seconds to warm up.
What do you call that piece of equipment?
This is GPR, ground penetrating radar. This, what is it?
But so is the other one.
Okay, yeah, I'm sorry, that's a very good question. This is an antenna of about 15. The difference between this one and what Mark Olson was showing is that his antenna has got a very low frequency. It was 400 megahertz or 300 or 600 or whatever. This is used for concrete for near surface. What he had there was for deep surfaces. So he was looking for maybe pipes or something that's about 15 feet down or 10 feet down or whatever. This particular piece of equipment is only for 16 inches depth. Okay, more than that, it's not the right antenna to use. You need a different type of equipment with a different antenna. I mean, it's still GPR, but it's just a different antenna. And so the antenna, the frequency determines the depth you can go with. This is good for concrete, near surface materials.
The lower frequency.
It's a much higher frequency.
Okay.
The one that Mark was talking about, the one that they were dragging on the dirt, that's used to try to figure out whether there's, pipes or something that's at about 10 feet, 20 feet, 30 feet. And, of course, please remember the accuracy of this thing goes down with depth. But anyway, this for concrete, for what we're talking about, is the best piece of equipment. And so I'll just show you here because it's kind of difficult. So this right now is a blank screen. So then I'm trying to find out whether there is concrete rebar in here. So I scan here and I'll hold it like this so people can see. These hyperbolas, you can see them, 1, 2, 3, 4. Those hyperbolas tell us where the rebar is. And when I was scanning, there's a light here. See, okay. There's a light here that determines where it is. So I place it over the actual location where it intersected, and that tells me where the rebar is. And sorry, we're doing this in the X direction. We could be doing it in the Y direction. So it'll tell us where the rebar, or mark it up on the slab or on the wall. The next bar, in this case, is approximately 18 inches away. I'm just reading off of the scale here. That's the next part. So we know the spacing of the rebar is 18 inches in this direction. Do it in the opposite direction, we get the same thing. So we get data on the X, Y directions for the rebar in the slab. It could be in a wall, it could be in a beam, whatever it might be. That is the beauty of this piece of equipment. It tells you also the depth. I showed that earlier slide. It tells you what the depth of the rebar is. For instance, in this one, the hyperbolas are showing to be at about 2 1/4 inches. So 2 1/4 inches down is the first layer of steel. Now there's a possibility there may be another layer, I'm not quite sure, but I'm not that sophisticated, by the way, with this equipment, as you probably can tell. But anyway, down below there may be another layer, and that'll be picked up. It's good for 16 inches in depth, this piece of equipment.
Can you reference the coordinates to real world coordinates?
Yeah, because you see this line here? When I'm moving it across the floor, that's the line. When I get to a peak, I draw a line. That tells me where that bar is. I move another 16 inches, that's another
But I
line.
mean to know where you are, GPS coordinates.
GPS coordinates.
You-
Oh,
You could
GPS and
mark that
GPR are.
anyway on the building, it's measuring.
They're not
Just mark
interested
it
in.
down.
No, this is
They just
the
you go along, you mark it right as you go.
local. Okay, I think this is probably enough, because I've got a few more things. We're running out of time. Sorry,
Yeah,
go
I
ahead.
mean, I'm not the one trying to rush us, but if we wanted to do the tour, I don't see him outside, so.
Okay, give me 10 minutes, I think I
Yeah,
can.
I think we can.
They use that for stud finding.
Oh, absolutely, yes. Yes, I mean, stud finders are a magnetic, works on magnetic. This is radar. Radar is, we talked about it, it's actually a very safe methodology. It has no, I showed you some slides of using X-rays. X-rays are a problem in that you need to vacate around the area when you shoot an X-ray. You need to, when we shoot an X-ray for concrete, like the slide I showed you, we need to vacate 20 feet around that area. So you can see in a building, if you're in a condo or something doing it, it's a bit of a problem, hassle trying to get people out. That's why hardly anybody uses X-ray in living spaces anymore. But so this is really the tool that we have now. It's 5 years ago, we asked to cart around something that big, and Mark Olson showed you some of those bigger pieces of equipment. They're too complicated. This is very simple, neat, it's very precise. We've never had any problems with it. So this is for our GPR.
How much is one of those handhelds cost?
This is about between $15,000 to $20,000. You want to buy this one?
Yeah.
$2,000, not so. It only works when I'm operating it, so I have to come with it. Okay, so ultrasonics. I don't want to take too long with this, but I want to show you this. This is very Now I'm going to use a prop that I had to use, unfortunately. It's not real world stuff, but it'll do. So we saw some issues previously with concrete when we were talking about the concrete at Cal, and we saw this really old concrete. It's got a lot of air voids in it, old stuff. They didn't know how to use vibrators. They were, so when they stripped the forms, I'll show you photographs a little bit later, but when they stripped the forms, they basically had a lot of air voids. Now, how do you test for these air voids? So what we do is we use this UT ultrasonic testing, and look at this. Okay. This is, again, a little bit of physics. So imagine this was a wall, okay? 12-inch wall, 50 feet long or whatever. And you stripped the forms, and there was some air voids in the concrete. You looked at, and you're now wondering, is this air void just on the surface, or is it within the concrete itself? So what you do is you bring these transducers, we call them pucks, you put one on each side, okay? And then they have to be lined up exactly. And this tells you whether the concrete is sound or not. So as a demonstration here, this is supposed to be a concrete wall, and it's got a hole in it inside. You can't see the hole. So, but as you scan from top to bottom, and I don't know if you can see this thing, the time goes up. Why does the time reading go up? The time reading goes up because now the sound wave that you're sending through here can no longer go through a material, it goes through air, and it takes much longer. So the sound wave attempts to go around the perimeter of the hole. That's the basis of this ultrasonic, a very powerful tool to try to determine what is inside a concrete placement, because you can't see inside. I mean, you're looking at a surface. I'll show you a photograph in a minute. But so this is ultrasonic testing. I mentioned earlier, we know the speed of sound through concrete is about 12,000 feet per second. So we know what the time should be. And if we get something much, much higher, let's say we get 50 milliseconds instead of 10 milliseconds, then we know there is a void there.
How
And
do
that-
you actually physically do that if it's like a slab?
I-
on the wall, where you can't
And
get
you
to
get on both
the
sides.
side?
Walls you can get to both sides, are basically over the top. And slabs, if you worst case scenario, you drill a hole and you put, we have, these come in 200-300 feet lengths, these cables. So you can go around all the way around.
But how do you see, like, how do you align it? If you're below the slab and someone's above the slab?
We have one of those, what do they call them? It's an infrared thing. You point it down and you can pick up from underneath where you're at. It's very powerful. It's a very good tool. Yes.
I'm more accustomed to seeing them being used, let's say, on the underside of the freeway where they're looking at the scene and trying to see if there's any
That makes sense.
voids or anything. So it's something where it's exposed on both sides. You can have either one technician do it in a small area, or you have two technicians coordinating that.
That makes sense.
Or make a jig or something.
Yeah.
Pass down.
Right, or you drill a hole and we make it, yeah, absolutely, Christina, that's a good point. And we use it primarily on, okay, the moisture meter, I'll just go through these meters quickly here and then we can do we have another 10 minutes, John? 10 minutes?
5 maybe? Yeah, 10 minutes is fine. He's not here yet, so
So I have
I
a,
don't really need to
this
rush.
is the Schmidt Hammer we saw earlier. It has a spring inside it. We talked about Hooke's law, the spring, etc. And on it here, there's graduations of what the rebound is, and then you can directly from that reading figure out what the compressive strength is. It's got a plus or minus, fairly high plus or minus, unfortunately, but it's a useful tool for comparison purposes. You got concrete here looks bad, concrete there looks better, so you can do a comparison. So this is the moisture meter I showed you earlier. We'll have a couple of prongs in here. I'm not going to demonstrate it because it takes so long. So prongs in here. These prongs go into the material you're looking to test. Typically, we use it for wood. As I showed here, the wood, it should be below 19% the moisture content. If it's higher than that, you've got potential dry rot problems. But anyway, the concept again is the same. They're sending a signal through one prong and picking it up with the other. So if the electrical current takes longer, then there is more moisture in there, then the reading will be higher. Like that says 13.1 versus 12.3. So this is the moisture meter. Very easy to use, very useful, I think, it's only, it's primarily used for wood, but it can also be used for chipboard and other materials. They're not as sophisticated for the other, but you would need different prongs. So these prongs are for wood. We have different prongs for chipboard and other softer materials. Okay, and then finally, I want to show you this borescope. Borescope is a very useful tool when it comes to trying to figure out what's inside a wall. Now, all these tools that we've spoken about so far have been non-destructive tools. No destruction. Everything's done on the surface, and there's no removal of anything to do. There's no coring, no removal of brick, etc. A borescope is almost non-destructive, but it has some destruction to it, and unfortunately that comes with the territory, but I'll show you in a slide in a minute how it can be used usefully. Okay, so the concept is to drill a small hole, 3/8 of an inch in diameter, in a wall, in a slab, and whatever it is. And you push this rod into that hole to look inside. So let's say a wall. This is typically where we use it. You've got a brick wall, wood wall. Brick walls are easier to explain because you've got the grout joints, and you can drill a hole through the grout joint, pretty much is non-destructive. And you put this in here, and you've got a light source. This attaches to a light source, which I don't have with me right now, but and then you put it in here, the cable, and then with the light source in place, you can now drill the hole. Let's say there's a concrete or a brick wall in it. And then you can look around. You can go 360 degrees all the way around and look inside that cavity. It can tell you if there's moisture in there, efflorescence, if you're looking for hold downs or something. Very good tool. It's not completely non-destructive, but it's as close as you can come to something without removing the element that you're looking at.
So there's a question about the slide you have up there. Why is the meter for the visible dry rot measuring 12.3? Shouldn't the number be higher than 13.1?
Excellent point. It's the dryness of the material that's the issue. This here, the prongs here that we're talking about, show 12.3. This is dry rot where there is actually little moisture. Yeah, there's been dry rot, but little moisture. This is a situation where there's no visible dry rot, but there's quite a bit of moisture. I mean, recent rains or whatever could have moistened the plywood, and you pick it up in moisture content, but it doesn't show. Dry rot, there's visible dry rot, but the wood is dry. Not much visible dry rot, but it's pretty wet. So that's a good question. Okay, let me just go to the next slide. Okay, here's some case studies. This is a project we did for ARG, and they were interested in. This is a bust, a bronze bust, and it is attached to this concrete base here. Okay, so the question was, what is the method of attachment of the bronze to the concrete? They didn't want to remove the concrete to find out. They wanted to transport this and place it in a new location. I think it's in San Francisco somewhere. But anyway, this is where GPR came in. We could, with the GPR, scanning the surface and the other four surfaces of this and the bottom of the concrete, determine whether there was something metallic. The point was there a dowel that attaches the bronze to the concrete, or was this bronze sitting on top of the concrete with maybe a mortar mix or glue or I don't know what, something like that. And we were able to find out that there were 4 rods inside that concrete that you can't see now, obviously. 4 rods, and they would come from the bottom of this pedestal all the way into the bronze statuette. So that's an application of where GPR came in useful. It wasn't the typical use where we're looking for rebar, etc., but this is a problem. Now here's another case study. This is post-tensioning. This is mainly for my structural friends. This is a slab, a concrete slab, prior to placement of the concrete. And what we see here in the blue lines are post-tensioning cables or tendons. And then the rest of the steel that we see, both longitudinal and orthogonal, those are mild steel, okay? And the reason why this picture is up here is because once this concrete is placed, you can no longer tell where the post-tensioning is, okay? GPR comes in extremely useful. You scan this top of this, just like I showed you earlier, and you can tell where these lines are. How do you know the difference between mild steel and post-tensioning cable? It's an engineering trick. You notice that these cables go up and down. They're at the top here, they go down, they go up. And that's because post-tensioning, the concept behind post-tensioning is to put compressive force into an area which is likely to see tension later on. So we use that trick when we use GPR to identify which is a cable versus which is mild steel. And why do we do all this? Because nowadays, a lot of construction is using post-tensioning. And by the way, you can tell this is post-tensioning because these cables are sticking out here. And then later on, after placing the concrete, and the concrete's hard, they come and pull these. And that's what the post-tensioning is about, and then burn off the ends of the cables. So the reason why we're doing this is because after the placement of the slab, owners and contractors want to come in and drill holes for whatever reason. Mostly it's to move plumbing lines around, etc. And this way, this method with the GPR, we can tell which is a post-tensioning cable and which is not. That way, when they do the drilling, and the structural engineer doesn't mind drilling through mild steel, which is normally what happens, it's okay. But you don't want to hit the post-tensioning cable. That post-tensioning cable, if it fails, it's going to cost between $50,000 to $30,000 to fix. It's a big, major problem. Okay, I'm almost at the end. Here is, sorry, go ahead.
When they put those post-tensioning cables in, you put them in and then you pour the concrete, and just before the concrete sets up, you tension it?
After the concrete sets. Typically, we have a requirement of so many PSI, let's say 3,000 PSI. So you're doing cylinders. Once it reaches 3,000 PSI, then you actually do the pulling. Yeah, I mean, that's typically how it's done. Then you remove the formwork from underneath. But it's a fabulous technique, post-tensioning. It saves a lot of money. If this slab had been all mild reinforced, it would be probably at least 25–30% thicker. So post-tensioning saves a lot of money. Okay, this is the situation.
To cut you off here, but he's on a time schedule.
One more slide.
One more? Okay.
This is a wall with adverse problems on the concrete surface. We talked about using the transducers with try to figure out whether there's voids inside. You can see the voids on the outside, but how do you know whether they're inside or not? That's where this comes in, the ultrasonic testing machine. Two quick things. This is actually for the benefit of our architects friends. This main issue here is when you have, oops, sorry about that. You have to go all the way back.
I can
Okay.
skip you ahead.
We need to move forward a bit. Okay, next one. So, oops, I'll skip the stucco one. Brick one is most important. Where do you use the boroscope? This is a good example where you use the boroscope. You can drill a hole through the mortar joint and look into the wall cavity. You can tell whether there's moisture on the inside. There's potentially bad mortar on the inside. There's potentially some condensation. That's why we would use the boroscope. Stucco, I'm just going to skip over this. This is the final slide. Case study, Hooke, Castle, Neptune Pool. Oh. Okay. We did this is for one of our clients. They were investigating the pool. This is marble here. And so we investigated the marble. We did petrographic examination, X-ray diffraction, etc., trying to figure out what the quality of the marble is. This is, of course, a historic building. These two are exudation. That's basically like the stalactite. It's calcium oxide that is carbonated, as hardened. So we did testing on that to make sure that there's nothing in those materials that is deleterious. And that's it. That's me. I just want to tell you one final thing. Yeah. This material that we put out as engineers, it's pretty staid. I think most of it is boring, to be honest with you. But anyway, I hope you enjoyed it. I got to tell you a joke. It's an engineer's joke. Maybe you'll like this, maybe you won't. I don't know. So this engineer passes away, and instead of going to heaven, he ends up in hell. Well, God is very upset. He picks up the direct line to Lucifer and says to him, Lucifer, you know that engineer you got there? That guy should be here in heaven, shouldn't be there in hell. Oh, Lucifer says to him, I'm not going to send this engineer back to you. This engineer is being so good to us. He's put air conditioning in here. He's put escalators in here. He's not coming back. No way is he coming back to you guys. God says to him, you don't understand. This guy belongs in heaven. And if you don't send him to heaven, I am going to sue you. Lucifer says to him, yeah, right. And where are you going to find a lawyer in heaven to sue me? Thank you very much.